Lesson 3.7. Today, what we're going to be looking at is using our calculators to create sine and cosine functions. But more than that, really, we could talk about that. I'm not going to be as high on lists and spreadsheets today because we've done that a number of times. Instead, what I'm going to be looking at is real world problems and how we turn that into equations. That's really what we're going to be looking at. So we're going to be constructing models. And today, we could rely on the calculator, but today I'm not going to try to do it as heavily on calculator. Okay, so let's begin. First, on example 1, it says the figure shows the depth of water along a seawall. The depth is 5 feet at low tide and 11 feet at high tide. Okay, I want to pause there. What can you tell me? This is describing if it says the depth is 5 feet at low tide.
That's the minimum.
That's the minimum. Okay, let's go ahead and make that mark here because that will matter for us, especially if we're not using the calculator. And 11 feet.
That will be the maximum.
At high tide. That's the maximum. Very good. On a given day, the low tide occurs at 6 a.m. and high tide at noon. That's telling you something else. Now, before you just yell out, I want everybody to think about this for a second. If low tide is at 6 a.m. and high tide at noon, that's giving you a time period. What's that referring to?
That's the period.
The period. Now, this wouldn't itself be one full period. It would be half a period. How do I know it's half a period?
Half a day.
Because, no. Because
not maxing.
it's not max to max. Very good, Asif. It's only min to max. So that'll be half the period.
So in 6 hours, half the period.
So 6 hours is half the period. So what's a full period?
12 hours.
Very good. Let's go ahead and put that. The period equals 12 hours. And that's because that is half of the period. That right there is half of a period. Because it's not max to max. That was low to max. Okay, so it says here, if D represents the depth of water. So notice, look at my equation. Pause, look at my equation. Where is D? Is D where we normally put it at the end of the equation? No. So since D is there at the front, I put C on the outside. Just heads up there. Maybe I should have used a K or something. But it says if D represents the depth of water. So this is our function D. T hours after midnight, use a cosine function of this model to complete for the depth of the water. Okay, so what could you tell me looking at the picture or using the map? What would be the formula to find, say, our amplitude?
For the max minus min.
Okay, so the amplitude, if you weren't going to use the picture, would be max, equal sign, max minus min. What's our max? 11 minus the minimum divided by 2. Okay, 11 minus 5 is 6. Divide that by 2, we get 3. Batista, you can figure it out now. Sit up for me, please. Now, what else can we use the max and the minimum divided by 2 to find? How about the midline? Okay, again, you could look at the picture and just see it, but just to have it down on paper, it's maximum plus the minimum divided by 2. Okay, so what is 11 plus 5? 16. Divide that by 2, we get 8. Yeah, there it is. That's the y equals 8. And I should have put y equals on the front. Y equals, there we go. Midline's always y equals. Okay, so by equation, that's A. This would normally be D, but in this equation, we're going to call it our C. The only thing left is the period. What's the formula for period?
2 pi divided by.
Yeah, so I'm going to substitute the word period with 2 pi divided by B. That's going to equal 12 hours. Mathematically, 12. To solve this, I'm going to cross multiply and divide. Make that a fraction here. B times 12. 12b equals 2 pi times 1. What is it? What variable am I trying to isolate? The b. We know what 12 is. We know what 2 is. We know what pi is. We don't know what b is. Let's solve for b. How do I get rid of this 12?
You
divide. That's why we call it cross multiply and divide. This can be simplified. We can now say that b is
1/6
pi divided by 6. And we should be able to have our equation now. Our equation would be d of t equals our amplitude. That's our A value. Let me put equals A here. And for this problem, we're going to say our midline is C. Equals 3 cosine pi over 6 times x plus 8. All right, I have a question for you. Why is it that they used a cosine function on this problem as opposed to a sine?
There's a transformation.
Because it starts at its maximum. Cosine begins at either its maximum or minimum. Sine begins at its midline, and left there is the transformation. All right, part B. It says use your model to find the intervals where the intervals of time where the tide is rising. Okay, so we could use this model. I'm actually going to use this graph on this part. Where are we increasing from? They told us actually in the problem. We don't increase starting at 6 a.m. We start increasing up until noon. On our first period, it's from 6 to noon, which means the intervals here, anytime, from 6 to 12 noon, this value would increase. Now, because of time, this is counting from 0 to 24 because there's 24 hours in a day. If you just went off the clock how we normally do it, like once you hit 12 to start back over at 1, this would be true for every round. If you look at it, 18 would refer to what time? 6 p.m. Whereas this is 6 a.m. But it's still true. Look what happens at 6 p.m. to midnight, 12 a.m. This is 12 a.m. This is 12 p.m. It's still increasing on that interval. That makes sense? All right. How about this? Example 2. Yeah.
How do you know the translation on? No, there is actually.
This one did not have a translation horizontally. It did have a translation vertically. The graph was shifted up 8 units from the midline is not on the x-axis. The parent function of sine and cosine had the midline on the x-axis. We do have a vertical translation to move this up to where the midline's up at y equals 8. But there's not a horizontal translation because the tide begins at its maximum. For cosine, there's no horizontal transformation. Now, if you want to write this as a sine function, then there would be a translation. Because remember, sine is supposed to start here at its midline. You see how this would be where sine begins? So on this one, if you want to use a sine function, you're saying, hey, the origin is supposed to be here. It's been shifted right 9. So inside the parentheses, you would need to have a -9 and its own parentheses with x. Here, I'll write it. How about that? Makes sense for you? If you want to use sine, you could say it's 3 sine. Now I'm going to do this bracket, pi over 6, x. To make something go right 9 units, do I do a +9 or -9? -9. Close both the parentheses and the brackets, then add 8. And now you have a sine function that represents the same data. So that would be sine with a horizontal translation right 9 units. Does that make sense? Okay. Like 9 is not very clear. Let's make that -9 again. All right. Let's look at example 2. The height above the ground of a yo-yo can be modeled by the equation h given there, where h represents the height of the yo-yo in feet above the ground, and t represents the time in seconds since the yo-yo was first dropped from its maximum height. Okay, one more time. If it drops from its maximum height, now this, they gave us the equation, but if it's dropped from its maximum height, which function makes more sense to choose? Cosine. Why cosine?
Because it starts from the max.
Because it starts from its max. Cosine starts at its maximum. Or if you want to have a vertical reflection, you can start it from its minimum. Okay. When does the yo-yo return to the maximum height for the first time? Now, how would I Explain that to me. This is what the function context of the title means.
So it wants to know how long the period takes.
It needs to know the period. All right, great. So how can I figure out what the period is? What do I use?
2 pi over.
So we're saying, what is the period? That's so the period's formula is 2 pi over b. I agree. It's going to be 2 pi divided by b. So what is our b in our problem? Looks like, or it is?
It is.
It is pi. Very good. So if our b is pi, then the formula is 2 pi. The period would equal 2 pi divided by pi. So, and 2 in this context refers to what? Let's add a unit to it.
Seconds.
In seconds. To me, doesn't seem practical.
But
if you have yo-yo, I think it goes a lot faster, unless you let it, you have one of those that spin. Have y'all yo-yoed much? Is that a white boy thing?
no, that's like a 90s thing.
I'm just joking. You can walk the dog? Nice. I never could do many tricks. I tried.
Always give me
Yeah, get knotted up. Yeah, I try to do the whole like bridge thing. You know, you see
Yeah,
people do. Oh man. Oh man. Bringing back childhood memories. How about part B? Find the maximum and minimum heights reached above the ground for the yo-yo. Now, using the equation, how could I figure out the maximum and minimum?
Just plug it in. So you do
Hey,
maximize
Dulce.
divided by 2 equals 2.5.
Dulce. Can you make sure you're here with me? We're taking, I hear a maximum and minimum.
So you would do max minus and then divided by 2 equals 1.5 and then you would algebra solve. So
okay.
1.5 times 2, which is 3.
How about this? If you were going to graph it, where would the midline be? Where would the middle of the yo-yo be?
2.25.
2.25. All right. And Christopher, I'm going to come to you here on this next question. So if this is the midline, that is y equals 2.25. From here, Christopher, how can we figure out what the maximum is and the minimum? The amplitude, very good. We add the amplitude and we subtract the amplitude. Very good. What is our amplitude on this problem? Max, yeah, that max will be the midline, which is 2.25 plus the amplitude of 1.5. And then how would I find the minimum, wherever that is?
Subtract 5 minus.
Yeah, that minimum would equal 2.25 minus the amplitude. All right, let's do our math here. 2.25 plus 1.5. 3.75. And finally, how about 2.25 minus 1.5? Okay, and what is our units this time? The max height. Are we in yards, feet, meters, kilometers? Feet. Okay, feet, there it is. And the minimum height would equal 0.75 feet above the ground. I'm going to go ahead and do above the ground. Above the ground. Add in the reference point. What is the reference point? It's above the ground. Let's see a little bonus work for you AP students here. If it's 0.75 feet above the ground, how many inches is that? Oh, very good. She didn't let me think very long on that one. That would be 9 inches. Okay, so someone else, how many total inches would 3.75 feet be?
How many inches?
Yeah, he does right.
45.
45, good. 3 times 12 is how much?
36.
36, add your 9. That would be, that's right. 45 inches above the ground. Okay. So now let's lead into where do you get sinusoidal functions so often in the real world? What applications do we have them in? And it's what we call simple harmonic motion. If you go into If you go into physics, you're going to get into this. An object that moves on a coordinate axis is in what we call simple harmonic motion. If its distance from the origin at time d, origin d, that's the distance, at time t is given by either of those equations. Now, this is going to walk through what you already know, amplitude, period, but there's this word I added in here. This lesson did not talk about it, but damped. I'm going to take a break real quick to show you what damping is. It's pretty cool. Damping happens very often in the real world. And so I want to show you this, even though it wasn't on the AP classroom side. Okay, I'm going to graph here y equals sine. What should it look like when I graph this? And I'm going to make it 5 just so it's bigger. Okay, you got that? Now, what I'm going to do is I'm going to show you what's called a damping factor. Instead of it just being 5, I'm now going to do 5x. Now, you're looking at it going, well, it looks totally different now. It does. I'm going to start to zoom out, though. And as I zoom out, you'll see it still has a pattern, and it's still wavy. Now, it is cool. Here's what the damping factor is. If you have what's a different function as your amplitude, 5x itself is a function. What type of function is 5x?
Linear.
Linear. If I were to graph that linear function, y equals 5x, notice what happens there. You see the maximum of each subsequent period would still hit that line. You see how that works? And just because sine and cosine, because they're waves that go positive and negative, if I did y equals negative 5x,
It would just reflect on the opposite.
it would show the minimums. Pretty neat, huh? We can go further, but I want to change my coefficient from a 5 because it'll get too big too fast. This time, I'm going to do 1/5. You see what 1/5 does? Now, why am I not matched up now? Okay, so if I change all these to 1/5, again, this will work. 1/5, 1/5, negative 1/5. And you might be going, okay, we knew that was going to work. Why did you do that? Because I wanted to actually make this x squared. Do you see how they still bound? They bind, if bound. Usually we say bound in math, but they bind, I think would be past tense. They bind this function in between. So this is what's called damping. Again, it's not on AP Classroom, but if you want to get into applied physics, which I think a lot of students who are math-minded, how many of y'all are science cluster? You might get into this and you might see some of this. So just to be aware, that's called damping. What that means is you're dealing with a sine function, but that sine function, the amplitude is that's getting multiplied by is a function in and of itself. And so the sine will follow that function that's being multiplied by. Pretty neat. I can make this 1/50 so it increases a little slower so we can see this better. Let's do that. It is pretty neat, isn't it? Where would that be used?
Yeah.
Okay. So where you might see that used, I'm following you. I'm following you.
You see it in the study?
Yeah. All right. So let's say you pick up a guitar. All right. If you pick up a guitar and you go to pluck one string, you've created, I would call it a cosine function, because when you pluck a string, I'm going to stand up here, you pull it up to its maximum and then you let it go. So it's going to start at its maximum. So it's a cosine. What happens is that it makes the sound because it creates that frequency of the wave bouncing back and forth. Does it go on forever?
No.
No, it slowly returns to the origin. What it means is in practical real world, because of whether it's, I don't know if on a guitar, if it would be friction. I don't know if it's air resistance. I don't know what it is that slows down that wire. I was not applied physics. But there is some physical tension that comes on to that slows it down. That would be a damped cosine wave. That cosine wave would damp to the origin. Does that make sense? So what could that look like? Let's see if I can get this right. No. I need to divide by x. Do I need to divide by x? Is that what I need to do?
Divide by x.
What do I need to do here? Give me a second here. I gotta get my. I came in. Let's see here.
Yeah, it would divert like that.
Yeah. So that's because that what I gave you the guitar. Well, now if you're looking at the center of the string right there on the guitar, if this is the guitar, it might be something like that. You might have a bigger number up here mathematically if you wanted to make it legit.
Isn't there like a weight on decibels that it'll like make a sound? I think based on your graph.
So it might be an idea like that. I'll get to you in a second. It might be an idea like that, but do you see how it's still each maximum of the wave is being bound in between? That's the idea. When you pluck the guitar string, it'd be something like that. Pretty neat stuff, huh? Okay. For AP Calculus, what did I see on their site? Did I see damping? No, I did not see damping, but I did see harmonic. What does harmonic mean? It means that it's an application of sine and cosine functions, things that are oscillating. What does oscillating mean? I'm using so many big words right now. Trying to sound smart because I'm not. You got the vocabulary, use it. What does oscillating mean, do you think?
Separate, but
moving. That's a good idea. Repeating in the same motion back and forth. Have y'all ever seen those like I do think it's with music. I've seen them or those they have and I've seen them on desks too. Like I interviewed one place and the person had them. I don't know if it's like a stress deal or a time, but it's like 4 hanging balls and you pull one and you pendulum. Thank you. And you let it go. What happens? It goes one side, hits the other ball, then it comes back, and it goes back like this, back and forth. That would be oscillating. It's oscillating back and forth. It's repeated motion. It's not taking some crazy path. You know, when a kid tries to play with them, they just, have them around. That would not be oscillating. But if you go straight in a line, you hit it, and it's just going back and forth, that's oscillating. It's returning back and forth, repeated motion. Okay. All that, it's here. This information, nothing's different mathematically. Frequency, they use the letter W. Do you know what W is in Greek? Let's check. Good thought, but that was a capital W. And it's a normal W, not a Greek W. This is a Greek W. They don't call it a W. They call it something else. Do you know what they call it?
No.
That's an omega. Yeah, they say the frequency is omega over 2 pi, whereas period is 2 pi divided by omega. Same formula. What have they exchanged? What letter is normally there? B. They exchange B with omega. There you go. All right. A point on the tip of a tuning fork vibrates in harmonic motion, described by the equation here. Find W for a tuning fork that has a frequency of 386 vibrations per second. Okay, here we go. How about this? 386 vibrations. And because I know the formula, I'm going to do it per, meaning divide, per 1 second. You're like, why did I write it out this way? I'm about to show you. They said that is the frequency. What normally is the formula for frequency?
It is
B divided by 2 pi.
B divided by 2 pi. When you deal with harmonic motion, instead of using B divided by 2 pi, they usually call B a different letter. It's the Greek omega. Yeah, which it looks like a W. W over 2 pi. How do you think we could solve this? Cross multiply. So 1 times W, that's easy. Omega, and that would be seconds. Omega seconds equals 386 times 2, all right? 2 times the 6 is a 12. Add 1 here. What's 2 times the 8? 16. Add the 1. 17. Add 1 here. 2 times 6 is 2 times 3 is 6. Add 1. 772. And this would be in vibrations. 386. What's up? Pi. Whoops. So the omega, if you were going to put that into the equation, it says leave in terms of pi. That would be our answer here. that would be our W is 772 pi vibrations per second. And this time, instead of dividing by 1, I'm just going to say like that. I'm thinking about this. The W might not actually take the variable might not actually take the units, but I'm going to leave them there. But 772 pi is really what you need to come up with on that. All right, so I've gone through 3 different real world examples. It's DOL time. Yep. Here we go. A ball on a spring is pulled 6 inches below its rest position, then released. The period for the motion is 4 seconds. Write an equation for the ball's simple harmonic motion. DOL number 1. All right, let's take a look at example 4. A mass oscillating. Here's that word again. Whoops, there it is. A mass oscillating up and down on the bottom of a spring. It says assuming perfect elasticity and no friction or air resistance can be modeled as harmonic motion. If the weight is displaced a maximum of 4 centimeters, if the weight is displaced a maximum of 4 centimeters and it requires 3 seconds to complete 1 cycle, find the modeling equation. Assume the object starts at rest. Okay, what is it telling us this time if we're assuming it starts at rest? This is a sine function. So it's sine because it's starting at its rest point. Now the maximum, what will that tell us?
That would tell us the amplitude.
It tells you our amplitude. Here is a question. If it starts at rest and it rises 4 centimeters, is it 4 minus 0 divided by 2?
No.
No, that rest is the midline. It's not. And this is telling us sine with the midline at 0. I'm going to go ahead and put that. Because it's a real world application, we can just say y equals 0. So this then would be giving us our A value, our amplitude. Our amplitude is 4. It requires 3 seconds to complete 1 cycle. What is that telling you?
That's the period.
That's the period. Very good. So if that's the period, we have a formula for period.
2 pi over whatever that omega is.
2 pi divided by omega. And if you put a b, I don't think anyone's going to complain. 2 pi divided by omega equals 3 seconds. All right, let's solve this. I'm going to leave off the unit this time. How do I solve that? Cross multiply. So I have 3 omegas equaling 2 pi. Divide by 3. So omega is 2 pi over 3. Let's write our equation then. We would say a mass, I'm going to call it M for mass, oscillating over time. M of t would equal, what's our A? 4 sine 2 pi divided by 3
T.
times t. There's our equation. Now, if you wanted to use a cosine function, you could, but then you would have to do a horizontal translation. Most things in the real world would be cosine functions because most things don't begin at rest and then somehow gain energy. Most things we have to perform energy on to get it to its maximum, and then it oscillates from there. So that's why most functions we give cosine because we give it the energy, and then the function itself, whatever it is you put the energy into, oscillates from there, whether it's a spring or whatever. All right, example 5. A Ferris wheel is constructed such that a person gets onto the ride at its lowest point, 5 feet above the ground, and rides, and the ride reaches its highest point of 125 feet above the ground. Let's pause. There's a lot of information. Let's just circle up as we go. 5 feet above the ground. That's the lowest point. What is that telling us? Min. Very good. I'm going to come back to you, Asa. Very good observation there. And the highest point is 125. That will be our max. We can figure out 2 values from this. What can we figure out?
Midline. Yep.
Very good. So the midline, by the way, it doesn't matter the order, but I just chose midline here, would be y equals, what's the formula?
Max plus minimum.
For midline, it's maximum plus the minimum divided by 2.
Which is 60.
130 divided by 2. 65. And this is technically in feet. The midline would be 65 feet. Okay. And you could also tell me the amplitude from this. Same information. The amplitude. What's different with our formula? I was putting the value. Whoops. 125 minus 5 divided by 2, which is 60. We'll go up 60 feet and down 60 feet from its midline. Okay, let's pick up the reading. I think I'm on this sentence. The amount of time it takes to complete 1 full rotation is equal to 8 minutes. What is that telling us? That's our period. What's the formula for period? And in this case, they do use a b, so let's use a b this time. 2 pi divided by b equals 8 minutes. All right. A little cross multiplication here. B times 8 is 8b. 2 pi doesn't have anything to multiply with, so you could do it over 1, but you still get 2 pi. Yeah, I can't even keep up with y'all this morning. So our b value, just like you said, 2 goes into 8 4 times. It would be pi divided by 4. Okay, now I'm going to go all the way back to the problem. Whoops. And Asa pointed something out. If they get on the ride, a person gets onto the ride at its minimum. If it gets on at its lowest point, what type of function is it? It's a cosine. Very good. And if it's a minimum, is it a positive cosine or a negative cosine? Negative. So let's write our equation here. It says the sketch. Whoops, we'll go out of order here. So A, we're going to say it's our amplitude, but we're going to make it negative because we start at the minimum. B, just to write all of our variables here, is pi over 4. If you get on at its minimum, does it have a horizontal translation? C is 0. And D is the midline value of 65. So here's our equation. They use a Y, sorry. Y equals negative 60 cosine. Since I don't have a C, I don't have to do both brackets. I can just say pi over 4 T. Sorry, let me scroll down. Plus 65. And I'll press the button to shoot it up more in a second. There we go. There's our equation. Now we were supposed to graph this. Let's do that. What was the minimum value? Where did we start graphing? 5. It looks like on the y-axis is counting by tens. So it goes to 5. And how much time did it take? 8 minutes to return? Okay, if it takes 8 minutes to go from minimum to minimum, how many minutes in will we get to our maximum? 4. And our maximum value was 130, if I remember right. 125? Okay, 125. All right, so in between, you would have the midline. I didn't even add the midline. What did we get as our equation for the midline? 65. We would hit that minimum at the halfway point between 0 minutes and 4 minutes, and y equals 65, sorry. We'd hit the midline, the halfway point between 0 minutes and 4 minutes, and the halfway point between 4 minutes and 8 minutes. How many minutes in do you hit that midline? and 6. And 2 minutes in, and 6 minutes in. Now, this looks like a perfect V. The tendency is for us to try to connect it as a straight line. Is this a straight line? Your movement on a Ferris wheel would be circular in nature. So when you graph it over time, what happens is it's rounded out. Your height actually rounds like that. And that's how this function would look. They have an X here. We need to change that to a T because our variable is T for time. Just going to change it to a T. At what time or times is the rider 65 feet above the ground? You already got that. 2 and 6 minutes. You know what, technically? Do you ride around the Ferris wheel more than one time?
Yeah.
Oh, I think you just go once and you get off. So that would be an endpoint. That's not what that would look like. All right. Example 6. Alternating current is a form in which electrical power is delivered to businesses and residents, and it's a form of electrical energy consumers typically use when they plug in television lights and any electrical appliance to a wall socket, like your cell phone or your headphones, or whatever. The current, I, in amps, flows through an alternating current circuit at time t is modeled by this equation. So part A, let's graph 2 periods of this function. All right, if it's sine, where does sine begin at? Origin. I do not have a vertical translation, but I do have a horizontal translation. Which way is this shifted? Barely to the right. So let's just barely move it to the right. I mean, this is such a small translation, you wouldn't even be able to hardly notice, but I'm going to do that. Now, it says graph 2 periods. We first got to figure out how much is 1 period. You take 2 pi and you divide it by what value? Which is 60 pi. When you divide that, 2 over 60 becomes 1 over 30. Okay, and if I want to do 2 periods, 1, 2, 3, 1, 2, 3. Let's just say this is 1 period right there. That needs to be 1 over 30. So I'm going to figure out the math here. If this is 1/30th, if that's 1/30th, the halfway point is actually 1/60th right there. That's where I would need to be shifted. This is going to be tricky, how to graph this. Okay, so this is going to be the half of 1/30th is 1/60th. When you do, if you think multiply 1/30th by, I don't know if I'm making sense right now. If you multiply this by 1/2, you get 1/60th. That's where we're going to begin. And so 1 whole period is this amount of distance, but since we're shifted right, it'll be right over here. That'll be the first period.
What?
Okay, sorry. 1 over 60. Oh, that's 1 over 360. My bad. Half that distance would be 1 over 120. We're still over here. I see why y'all are throwing off. I'm going to leave 1 over 60 there because that's where it is. We're still somewhere over here. Jeez. So instead of having 1 period complete right there, we're still going to be just to the right of it. How about that?
Let's just ignore the transformation.
Yeah, that's just difficult. The maximum. Where do we achieve the maximum?
Add 220 to the
and you know, one point we can add. This is going to go maximum back to 0 here. Now the 0 is shifted, so just shift that as well, just to the right of the midpoint. So if we start just to the right, here's halfway, 1/30th, go just to the right. That'll be the 0 on the way down. And then this will be the 0 on as we start approaching again. Okay, so the halfway point between here, we get our maximum. So somewhere in between these 2 points, which I think is around there, we get to 220. What are these counting by? They're counting by 20s. Perfect. So we go up to 220 and we plot our point. This is going to be great. Does that look like about halfway between? Are y'all okay with that? Okay. And then we'll also have a key point halfway between these two, somewhere in there, at negative 220. Okay, let's connect these. No, I'm gonna keep going. 0, another halfway point. Let's go 3/60ths. That would be 1/20. Sorry. This is weird with the fractions. This would be 1/20th. That's where the next maximum would be. And then 1, 2, 3. And of course, to keep our fractions going crazy, this would be 1/15. We would hit just to the right of 1/15. Okay, now I'm going to connect those points. What a graph. What a graph. I see this on the test. Messed up at the end. Forgot where I was going. I definitely messed that up somewhere in there, but one period. I think I need to come up and down in there and then back around. Yeah, I definitely messed up this second part. It wasn't obvious from the drawing. I think it's supposed to come back down and back up all within right there. So I'm gonna do it like that. I think that's basically what the graph's supposed to look like. It's not very pretty. All right, let's fill in the parts that are easier to solve for. What is our amplitude on this problem? That's ugly. Let's try this again. 220. We already found the period. What's our period?
It's gonna be 1/30.
1/30, and this is talking in seconds. It's 1/30th of a second to have a full wave. And our phase shift. What is our phase shift?
1/360.
Which direction?
Right.
Right. 1/360 to the right. Where are the x-intercepts of the function? What do they represent in context to the current? They're everywhere. It would be, this one would be 1/60th plus 1/360, which I think is 7/360ths. You'd have 7/360ths of a second. Now, what is it? Okay, here's the point right here. 1/60 is where it should have a 0. We have a shift that's 1/360th. If you take 1/60th
times 6
and you plus 1/360th, you have to get a common denominator. How do you get a common denominator? You multiply by a weird looking 1.
6/6.
In this case, it's 6 times 6/6. It's a weird looking 1. That gives me 360. And so I have 6 times 1, which is 6 plus 1, 7/360. That's where I got that. 7/360, 7/360ths of a second would be the first x-intercept. The next one would be 1/30th plus 1/360. So 1/30th plus 1/360. What funny looking 1 am I going to multiply by this time? 12. Very good. You would multiply by 12. So this time, the second 0 would be, what are you going to get there? 13/360 of a second. And now you can see the pattern because it's a period and it's a pattern. What is my numerator increasing by each time? 6. So the next one would be 19/360 of a second and so on. And I'll just do ... Okay, so what does it represent in the context of the problem? It's where our current changes from positive to negative. With electricity, you have a positive current and a negative current, and they flip-flop very fast. It's the change of positive to negative current of electricity. So electricity is alternating, which means it's a positive current, negative current, positive current, negative current. It's the change of positive to negative current. That's what the zeros represent. All right, after all that, we get to DOL number 2.
More like
All right, as you finish up DOL number 2, I'm now going to take a look at example 7 here. It says hurricanes are categorized using a Saffir-Simpson hurricane scale. Whoops. The table represents the number of major hurricanes in the Atlantic Basin that are rated as major storms of category 3, 4, or 5 for each decade from 1921 through 2020. Part A, we're going to use a graphing utility to create a scatter plot of data for t equals 1 through t equals 10 for the decades shown. Again, this t equals 1 here would be the first decade, second decade, third, fourth, fifth, sixth, seventh, eighth, ninth, and 10th. That's the idea here. So I want to open up my calculator, and I'm going to go to lists and spreadsheets. In lesson spreadsheets, the decades here, I'll put as D so I can keep track of that. And the hurricanes I'm going to do is H. So I have a first decade, second, third, fourth, fifth, sixth, seventh, eighth, ninth, and 10th decade. I have 10 decades to work with. We had 5 major hurricanes, 8, 10, 8, 6, 4, 5, 5, 11, and 9. Okay, so now that I have all my data in, what we need to do is it says create a scatter plot. So the way to do that is we hit Control Doc, we add a page. I want to go to data and statistics. Now in here, you can create a lot of different data. I want to remind you though, for us that whenever we're using data and statistics, we'll always have the variable, the independent variable, which in this case is decades on the x-axis. But the y's can change depending on what we're trying to find. This one just wants a routine scatter plot, so I want to put H. So this shows me a scatter plot. So that is part A. I wanted to find the scatter plot. I've done that. Let me take a picture of that so I have it for later. Okay, so now that I've done that, I'm just going to hit a little check here. It says find a sinusoidal regression function that best models the data. So I'm going to come back over here and I'm going to create sinusoidal function regression. So you can do it from lists and spreadsheets. The way to do it, let me make sure I got that data right. Is 8 supposed to be? That's 10, 9, 8. Oh, it is 5. Okay, it just looks like it's off. What I'm going to do here is go menu, analyze. I'm going to choose regression. And we know it's sinusoidal, it's periodic. Whoops, I chose the wrong one. Let's try this again. Menu, analyze. All right. And I want to choose sinusoidal. There it is. Hey. I wish I could delete that. How do I delete it? Let me get this one off the screen too. All right, one more time. Analyze, regression, show sinusoidal. And I want to change that to radians. So there's our sinusoidal regression. As you look at this equation, that is quite a crazy regression equation. That's hard to see right there. So what I'm going to do now is, now that I've taken it and listed spreadsheets, I'm also going to show you, excuse me, I said that wrong. Now that I found this in data and statistics, I'm going to go over to lists and spreadsheets and find it there. It'll be easier to see the equation. So statistics, stat calculations, and we're going to show the sinusoidal regression. The X list was D. The dependent was H. We're saving this as F1. So here's our function. And they show me my equation here. It's the same equation we've been working, except they have a plus C here in this equation. So we'll write this out. This so we can see all of our data. And I'll take a picture of this and add it in. All right, so the equation, I'm going to round to the nearest hundredth, would be y equals 3.06 sine. And then they do not use the brackets followed by parentheses. They include the b and the c together. So 0.97x minus 1 point, this will become 1.50. And the d is plus 6.67. So there is our equation. I know that's a mouthful of an equation right there. And that's the equation we could use there on part B. And since I'm here, I'm going to go ahead and here's our scatter plot. I'll do it like that. Okay. Now, moving on. It says on part C, what is the maximum and minimum number of storms based on your model? And so to find that, the easiest way now would be to add another page. And let's now look at the graph. So I'm going to go to graph. I'm going to press the up arrow, just go to F1 where it has my equation. And I'm going to zoom out this way. And because this is periodic, it has the same maximums and minimums repeated. So I don't have to find all the maximums. I'm just going to find one. So I'm going to go menu, analyze graph, choose maximum. And my maximum occurs here. It appears it'll be around 10 major hurricanes per decade. The minimum, analyze graph minimum, we could use the very beginning, but I'm just going to go right here, would be about 3.6. So I'm going to add this in now. Because these are talking about major hurricanes, you can't have 0.73 of a major hurricane. I'm going to say, according to the model, the maximum amount of major hurricanes per decade is about 10. Again, because you can't have 9.73 hurricanes. And the same with the minimum, because I'm just because I know that rounds up to 4, but because we're talking about hurricanes and we're talking about the minimum, it appears to me that we might have as few as 3. So same is true here, except the minimum, when we do the minimum major hurricanes would be 3. And that, again, that'd be per decade. Now, when you look back at this data from the previous slide here, you might notice that we had a decade that had 11, but we're talking about according to the model. So even though that's 11 there, even though the data itself says 11, we're going to go off our model that predicted about 10. That would be an anomaly there. Okay, so in part D, it says, in what decade will the next maximum number of stores occur based on your model? Well, we've gone till 10. Let's see when the next one is. So the next model would be in the, let's see, menu, analyze, maximum. The next would occur, and that's decade 9.56. So we need to slide over, and we'll say, analyze, in about the 16th decade would be the answer here. The next maximum number of major hurricanes would occur in the 16th decade. And we could go off the previous page. If this is decade 10 here, if you add 6 more decades, that would get us till 2080. So that would be 2071 through 2080. Let's hope that's true. Finally, DOL number 3. So this is going to be multiple part for you. We can conclude here. You can use this data to come up all your information. You need to plot a scatter plot. You can do that on part C and D's page, this next slide right here. And then finally, you're going to make some observations from your model here. DOL number 3.